Okay. Hi, my name is Sam Miller from NASA Langley Research Center, and I'm going to be talking to you today about this idea that I call robot ecologies. It's kind of a compilation of ideas I've gleaned from other places. I think what I want to talk about is robots and ways of thinking about them that I think we need to change the way we look at them. A couple things. These are like the axioms of what I think we should do is, instead of thinking of one fancy robot that can do everything, think of many robots that can do specific things. Instead of having robots that can specifically recognize laptops and tables and know how to avoid them, we need to think of behaviors, which are simple mappings from inputs on the sensors to outputs. Instead of thinking about communication-oriented systems that have to have fancy protocols and know how to talk to each other, I think we need to think of robots as interacting with their environment. The environment is the media by which they talk to each other. Instead of thinking about emergent behavior, I know I'm kind of bucking the system here, I think that doesn't work. Complexity thrown into a room does not equal intelligence. I think instead we need to design a system with a function and make the individual components so that that function emerges out of their interactions. So here's my example. My cursor's in the middle there, but the idea here is this is a room, and the room is populated with a bunch of little robots that will crop up here in a minute. This little guy is about the size of a gecko. It's not super realistic, but he has a couple little whiskers, and his entire universe is corners. He lives in corners and gets rid of pesky cobwebs. So, not complicated. He follows corners. You know, maybe he has some solar power or something like that. Here's his partner, if you will, totally disconnected. This is a little bigger than a quarter. Kind of a stupid little stochastic thing. All it knows is don't fall off the edge and go back to the edge. You put this on your table, your bookshelf, your windowsill, whatever. He just lives there and he pushes junk off the edge. That's his universe. This guy's a little smaller. He lives down by the corners of the floor. He hugs the wall. He goes behind your drawings. He collects dirt, hoards it up inside of him until he's full, and then periodically he goes out and dumps it in the middle of the floor. So he keeps the edge clean. So then here's the kicker. That's all fake, right? Well, that's not fake. That's real. You can buy one of those. That's a Roomba. It really does a good job in my robotics lab. That's what keeps the floor clean, and it does a really good job at it. So what I've just shown you is a set of robots that are communicating, but they're communicating through the environment. They don't have any high-level purpose, but they're still accomplishing a task, which is keeping this office space clean. And I think we need to think about robotic systems like this, and I'll touch on it a little more in the future. So I like this definition that an ecology is a totality or pattern of relations between organisms and their environment. I think we have a couple examples of these. Obviously in nature we have ecologies. That's where the word came from. Ecologies in nature kind of perpetuate themselves. I think you can also take that discipline and you can talk about it in terms of building a bridge or an aircraft carrier. There's a critical difference though. In those applications, there's intelligence and purpose on the part of the designers. They know what they're doing, whereas in nature, the mouse doesn't know that the hawk is getting it and then it has to escape, or the ants or whatever. So I think if we take those, there are a few principles that we can extract about how to design robots that will fundamentally allow us to accomplish high-level goals without the systems being intelligent themselves. The first is the recognition that the organisms in this ecology, they need to be distinct in role. They need to be disparate in the methods that they use to accomplish their particular job. And probably most importantly, they need to be sized appropriately. Ants do their job, hawks do their job, elephants do their job. If we think about the system of how these organisms interact, I think it's important to recognize they don't have common intelligence and direction. They don't have a common language. They can have a common language, but it's not necessary for functionality. Finally, they are designed as unified in purpose, although they don't know it. So I showed you kind of a make-believe example. This is another make-believe example that's maybe a little bit more interesting. It's kind of building a habitat on the lunar surface. So you've got lots of little robots that are running around, lots of different ones. This one, maybe he does exploration. And this is all notional. This is never going to be on the moon or anything. But you know, you got these other guys that can maybe scoop up dirt and put it in other ones. You see what they're building in the background there, some kind of a habitat. But there's robots of different sizes. Like for instance, this one that's coming up here in a second is a very large robot. It's taking lunar regolith in and it's spitting out bales of regolith on the other side. There's these systems of little robots that can collect those up and they autonomously follow each other, and all they know is we pick up bales and we take them to the place where the construction's happening. So they're not real smart. Maybe they have a little bit of communication, but They don't need to have a lot. Then there's this guy. His entire universe is picking up bales that are next to the construction site and stacking them in an igloo to protect future astronauts who might show up against solar flares. So all these systems, they're loosely coupled. Maybe they have a little bit of communication for health status or something like that. But maybe there's inspection robots, etc. Got to cut it off now. So why do you care? That's true. There's 30,000 robots in Iraq. There's Roombas. I think we need to make tools that will allow these to be less robotic and more interactive. LabVIEW works with SolidWorks to program parametric CAD. And I think this is the physical embodiment of object-oriented programming. So we can talk about it more if you like.